We noticed that when we worked with both circles and ellipses, when we put cosine in the y position and sine in the x position, they would start at the top and work clockwise, which means that we can actually turn an equation into the equation for a clock, which is what we're going to do in this problem. We all love clocks. They're so much more fun to watch. All right, so let's model the motion of the tip of the second hand of the clock, which is 15 inches long, moving smoothly around the face. Sorry, my face got a little wobbly there. And once every 60 seconds. So it moves once every 60 seconds around the clock face. Let the center of the clock be at the origin. Sure, why wouldn't you? I mean, that's just smart thinking, right? So you're going to make the center at 0, 0. And we're going to create parametric equations for that circular path. All right, so let's start off with the parametric equation, which we kind of know how this is going to work when it's with respect to theta. So the parametric equation with respect to the angle, with respect to angle theta, that we already know because it's in our standard form from a couple pages ago, right? Or honestly, it's this one right here for an ellipse. It's just that A and B will be the same, right? And H and K will both be 0 because we let the origin be our center. So that means that it's going to be 15, because it's 15 inches long. See that right there? So 15 sine of theta, comma, 15 cosine of theta. Ta-da! And we know we want one time around the clock. So because we want one revolution, that's what we're going to use. Right? What makes a circle as opposed to an ellipse is that you have the same number in front. So 15 and 15. So in an ellipse, there'll be different numbers. In a circle, they'll be the same number, which keeps your radius consistent all the way through. Right? So a circle is like a special type of ellipse. Okay, this is all well and good, but this is not what we want. Right? So we want a parametric equation that describes the circular path the tip follows, but we haven't used the fact that it has time. So we need time, right? Let me write that down. So this is correct, but not enough. This makes it so it's that circular face. It's the clock portion we want, but it's not necessarily moving at the speed that we want, right? So we need to introduce time. All right, well, let's think. One revolution would be 0 is less than or equal to theta, which is less than or equal to 2 pi. But that's also 0 is less than or equal to time, which is less than or equal to 60 seconds. Because on a clock, since we're working with the second hand, it would take 60 seconds to move all the way around, as opposed to the hour hand, which would take 12 hours. All right, that means that we can set up a relationship. So theta is to time as 2 pi is to 60. Right? Theta is to time as 2 pi is to 60. Or you can say theta is to 2 pi as t is to 60. And it'll work either way. It's a proportion, right? So we're setting up a proportional reasoning here. All right. So that means that, well, I want to solve this for theta because I want to be able to substitute in here. I have too many so's here. That implies, let me put a little that implies arrow. Theta is equal to pi over 30 times t. All right. So then I can take that and substitute it in here. So the parametric equations with respect to time for a clock would be 15 sine of that theta, which is pi t over 30. Of course, t over 30 came because 2 goes into 60. And then 15 cosine of pi t over 30. And I would let my parameter go from 0 to 60 because, of course, I want to stop at 60 seconds. because I'm going to travel one time around the face of this clock. That is a parametric equation for a circle, well, for the clock face. And I can see it in Desmos if you're interested. We're probably not going to watch it travel around, but there you have it, right? So you can see the circle, x squared plus y squared equals 15 squared, which is 225. And then 15 sine, right, 15 cosine. So if you want to see it get drawn, instead of just looking at it, there it is, right? Oop, I have to put that in there. And then I have to let this go to 60. It was stopping at 2 pi, which is not what we wanted. There you have it. Beautiful. All right, so that's one of the many applications that we can use for a parametric equation with a circle or an ellipse.